Hi students, today we are going to discuss in detail about the mechanical properties of dental materials. This chapter focuses on the effect of mechanical deformation or how materials behave under applied load or a force. So this chapter is very important to study or understand the properties of materials or dental materials as they are experiencing a lot of loads inside the oral cavity such as during mastication and during other functions. First, let us talk about what is stress. Stress refers to force applied per unit area that arises within a material as a result of externally applied forces. So stress is given this formula, or it is measured by the total force, which is measured in newtons, by the surface area, which is measured in meter squared. So the unit for stress is Newton per meter squared. We have different types of stresses, including tension, when the material is being pulled, compression, when the material is undergoing a compression force, shear, as in when two materials are rubbing over each other or when two forces are acting into opposite directions to tear a material apart. Friction refers to the bending of a material, and the stresses which are created in a material as a result of flexion is called flexural stress. And this stress is usually measured by using two supporting points, and so it is called as a 2-point or a 3-point bend test. As a result of stress, the material undergoes some deformation, and this deformation can be either elongation or compression. So when there is a change in dimension of a material, this resultant change in dimension is called as strain. Usually, this is referred to as the change in length by the original length. So this is a measure of the percentage of elongation a material undergoes with the applied load. So strain is the deformation of a material from stress. It is simply the ratio of change in length to the original length. So since both the numerator and denominator are in the same metrics, there are no units for strain. Usually strain is expressed as a percentage. Both stress and strain and the material deformation properties can be calculated using this machine called universal testing machine. To simply put it, the universal testing machine has two jaws, the upper and the lower jaw, to which any material sample can be attached. And when force is applied, a predetermined force is applied to this material, the computer which is there next to this machine is going to calculate the strain, and so we get the force per unit area or the stress built up in the material. So this graph is called as a stress by strain graph, where stress is expressed in megapascals and strain is expressed as a percentage. Let us just see how this graph develops. Say first the material undergoes a small amount of stress, and there is this plot which comes on this graph. Similarly, the machine keeps applying loads till a point where there is a uniform, till the point where we get a uniform straight curve, straight line. So this line is a straight slope, and it is the line which expresses the modulus of elasticity, and till this point the slope or the curve remains a straight line. This indicates that till this point, the red mark which is seen here, the stress by strain remains a constant. And this constant is called as elastic modulus. The property of rigidity of a material is given by this stress by strain or the modulus of elasticity. So this means that materials which have a high elastic modulus do not deform easily, or they are more rigid, which means applying a large amount of stress will create a very less strain in the material. Hence, the modulus of elasticity is very high, which means the material is more rigid. So you can see the table which indicates the elastic modulus of common materials and the enamel and dentine here. You can see that the elastic modulus of enamel is much higher compared to the dentine, which means enamel does not deform as much as dentine. So what happens to the material if we continue to apply forces beyond this point, which is shown as red? This red point is called as a proportional limit because it is only till this point that the stress and strain are proportional. If we continue to apply force beyond this limit, we have another point called as the elastic limit. This limit signifies the point till which the material can come back to its original shape when the force is released. So you can imagine this like a rubber band which is being pulled to a particular point, and when you leave this come back to the original shape without any deformation. So the same thing is exhibited by all materials where till the elastic limit the material comes back to its original shape when the forces are stopped. So if we continue to apply force beyond this elastic limit, there is a permanent deformation of the material, which means the curve is no more straight and the material does not return back to its original shape. So the curve becomes slightly deformed, or it is no more straight as in the proportional limit, as till the proportional limit. If we continue to apply force beyond this, the material fractures, and the point of fracture of the material is called as the ultimate strength of the material. In some cases, we will not be able to differentiate the straight or the curved portion of the graph clearly. So in these cases, to clearly differentiate the point of elastic limit, another measure called as yield strength is used. This is usually drawn as a line which is parallel to the straight portion of the curve, and the point where this curve meets the straight line is called as the yield strength. So it is used sometimes as a replacement or an alternative to the point of elastic limit. Next, the area of the curve till the proportional limit is called uh, the resilience of the material, which means the material's ability to absorb forces and spring back. And the total area under the curve is called the toughness, or how much of total energy is required to fracture the material. So these two are very important properties. So the curve, the area A and B represent the resilience, and A plus B represents the toughness. So depending on the type of stress applied, we can calculate this ultimate strength as compressive strength, tensile strength, or flexural strength. So this is a curve which shows the property of enamel and dentine under load. You can see that the enamel has a proportional limit of 235 MPa and a fracture strength of 262 MPa. Similarly, dentine has a proportional limit of 176 MPa and a fracture strength of, or a compressive stress of 234 MPa. What is Poisson's ratio? Poisson's ratio refers to it measures the material property or a tendency to deform in directions perpendicular to an applied force. For example, when a material is stretched, as you saw in the rubber band, it gets longer and thinner. So the change in the strain in two perpendicular directions is calculated as the Poisson's ratio. So Poisson's ratio measures the deformation of a material in the direction perpendicular to the direction of force applied. So this is the formula. You don't have to remember too much of formula in this, just know the concept, that will be sufficient. As I told you before, the flexural strength can be measured in a 3-point bend test, and this type of strength is called as flexure strength. Flexibility is also measured in the same manner, but it refers to the amount of deformation a material can undergo when subjected to flexural forces. So the more the material deforms during flexion, the more the flexibility. At the same time, the flexibility should be such that it can, when the forces are stopped, it returns to its original dimension without any permanent deformation. The other type of strength is called as the fatigue strength. This type of strength is very important because unlike the static loads or single loads applied which we saw in the previous measurements, here the loads are cyclic, which means the same material is subjected to a variety of loads over a period of time. So this cyclic loading helps, or it tries to simulate the oral conditions or the act of chewing and repeated loading inside the oral cavity. So this is always calculated in cycles, or 10 million cycles will represent almost 10 years of intraoral use of the material. The next strength is called as the impact strength, and impact strength is the ability of a material to absorb the energy and resist fracture when subjected to a sudden applied load. Sometimes the materials inside the oral cavity can experience a shock or an impact, and the ability of the material to resist such impacts is called as the impact strength. So usually there are different methods for testing the impact strength. One method is called as the ISOT test, and the second method is called as a Sharpie test, where both there is an accelerated load which is coming and falling on the specimen, and this measures the amount of force required to break the specimen. Fracture toughness is a material's property to or the ability of a material to resist the growth of cracks or flaws under stress. For example, you have a material which is shown here. This is a zirconia which has a small crack. So this zirconia material, it resists deformation by a phase transformation called transformation toughening. So here the tetragonal zirconia, which is shown in green color, transform into monoclinic form or the yellow color, thereby making the material much more tougher. So this makes the material less resistant to crack propagation, and the material has a very high fracture toughness. Next we come to the measure of hardness. Hardness is a measure of the resistance to local indentation by a material. So this is a surface property, unlike the previous properties which we saw. So this refers to how hard the surface of a material is to scratches or wear. Hardness is usually measured in a scale from 1 to 10, and this scale is called as Mohs hardness scale, where diamond is the hardest material and talc is the least hard material, and we have other dental materials in between the scale of 1 to 10. Hardness is generally tested using various types of indenters. Some indenters can be a round steel ball with a various diameter as shown in Brinell hardness. Usually a steel ball of 10 mm diameter is used. The Knoop hardness uses a pyramidal shaped indenter, and the Wicker hardness uses a 136-degree pyramidal indenter. Though the indenter is different, the method by which the testing is done is almost the same, where the indenter is left to a force is applied and the indenter creates an indentation on the surface. We can calculate either the length and width of this indentation or the diameter of this indentation if it is a circular indenter to calculate and arrive at a hardness number. So Brinell and Rockwell use a large indenter and heavy force, and so they are called macro hardness tests. Vickers and Knoop typically engage forces which are less than 9.8 newtons, and so they are called micro hardness tests. Barcode and Shore tests are commonly used in dental materials which are very soft, especially Shore hardness is a test which can be used for testing elastomers, rubbers, or soft silicon materials which cannot be subjected to the regular hardness test as shown before. Malleability and ductility. Malleability refers to the ability of a material to be beaten into sheets or thin paper. Ductility refers to the ability of a material to be drawn into a wire. So copper is a very highly ductile material. The most malleable and ductile material is gold. Ductility can be measured as a measure of percentage elongation, or you can bend the material into 90-degree bends to see when it fractures. This test is called as cold bend test, or it can also be a measure of reduction in the total surface area. With this, we come to the end of this chapter. Thank you.